In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 70. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with nature of water content associated with transformer oil. There are three types of water content, that is one, dissolved water, emulsified water, free water. These three. Dissolved water refers to water molecules that are chemically absorbed and evenly dispersed within the oil. Most of the water in transformer oil would have to exist in the form of dissolved water whose amount is to be increased with increasing temperature. But there would have no visible indication present until the water molecules have become saturated in oil. Then emulsified water. Emulsified water is chemically bound water whose very small droplets that are to be dispersed in oil at higher temperature. That form is normally found in aged oil. Oil viscosity would have become higher with having cloudy and milky appearance. Emulsified water would have a greater impact on breakdown voltage than that of dissolved water. Free water. Free water is also supersaturated in solution, but in a high enough concentration to form water droplets and separate from the oil. Free water, as it is being phased out of the oil by force of gravity, so free water is visually apparent. Its presence can significantly impair the ability of the oil to withstand electrical stress, causing to increase the risk of partial discharges, arcing, and ultimately a complete electrical breakdown. At elevated temperatures, free water would have to form bubbles, which can further reduce the dielectric strength of the solid and liquid insulation system. Even an insignificant amount of moisture or water molecule in transformer oil can cause of more hazardous effect than any other impurity. Slightest possibility of moisture in oil that can not only affect the dielectric performance of the oil itself, but at the same time typically affects the dielectric performance of the solid insulations as immersed in that oil. However, deterioration of the dielectric performance of the liquid insulation that would have to vary in regards to varying degree of water solubility in that insulating liquid. The degree of water solubility is expressed as the total amount of water that can be dissolved in the oil at a specific temperature. Solubility of water in insulating oil is never be constant, and that would have to increase sharply with the increasing temperature. See the diagram? That is graphical representation, water solubility in mineral oil and temperature. In figure 194, where it is shown that the level of water solubility for mineral oil as corresponds to the rise of temperature is not linear but exponential in function. So, the amount of water content that can be dissolved abruptly in oil with the increase of temperature. If the operating temperature of transformer is somehow to be in higher side, then the amount of water that can be dissolved in the oil would also be increased tremendously. While temperature comes down to normal operating temperature, that is on at cooling cycle, that dissolved moisture as accumulated in the oil would have become in supersaturated condition. At the same time, the state of the water content is then changed from dissolved state to emulsified or free water state. It is obvious that the breakdown voltage of the transformer oil depends not only on the water content but also on the state in which the water molecule exists in the oil. Emulsified state of water would, would have the more potential hazard for dielectric strength of the oil than that of the dissolved water. It is as because that the dissolved water would always be in oil at highly dispersed state, and there would have uniform distribution of the water molecules in the oil. In this state, it is rather difficult to form consecutive conductive bridges in shorter wavelength under the action of the electric field. But in case of emulsified water, with suspended small water droplets in oil, is quite susceptible to polarize under the action of the electric field, causing to form a series of elongated conductive bridges. Most important. As the conductivity of these bridges is comparatively be larger, so it would lead to increase the corresponding leakage current, causing to generate an abnormal heat. Finally, that heat would create a free breakdown of these small bridge channels, which is called as thermal breakdown. And once it is started within the oil, that would force to distort the electric field distribution in the oil. Again, I repeat, finally, that heat would create a free breakdown of these small bridge channels, which is called as thermal breakdown. And once it is started within the oil, that would force to distort the electric field distribution system in the oil. Such occurrence is not only affect the usual electrohydrodynamic and kinetic nature of the oil flow system, but also would have a significant effect on the dielectric strength reduction of the insulating oil. Therefore, the effect of electric field on the water oil interface is highly complex, and that would have to vary with the change of water content physical state. However, it is quite evident that presence of water droplets are the most dangerous impurity, as because these are typically distributed throughout the entire volume of a liquid dielectric. When voltage is applied, there would have to occur polarization of water molecules which are being oriented by the electric field vector direction, and there may have to form chains with increased conductivity. Occurrence of electrical breakdown would have to start along these chains. The presence of moisture in oil that would have to act as charge carriers, and for which the breakdown voltage of dielectric fluid is to be decreased with an increase of moisture content in it. As of a thumb rule, it is to be noted that if there would have been only 0.01% presence of moisture content in volume of transformer oil, then the dielectric strength would immediately be decreased to 3 times. The interactions between insulating oil and windings can lead to contamination, which will accelerate chemical reactions at high operating temperatures and thus to deviate from the original properties of the insulating oil. The electrical, physical, and chemical characteristics of the liquid dielectric should have to be periodically tested for determining whether the liquid dielectric at all being favorable to be used further in service for transformer applications. With the assistance of the most preferred test method as applied in Fourier transform infrared spectroscopy, FTIR rather, technique based on absorption band, it has been correctly revealed that the chemical composition of transformer insulating oil is also been affected due to the presence of water content and temperature. The electrical and chemical properties of mineral oil based insulating fluid as used in transformer would have been assessed according to the standards IEC 60156 2012 and ASTM D2144 07 2013. Now, bubbling phenomena in oil field transformer, most dangerous. It is obvious that the combined effect of the amount of water content, the temperature of the insulating system, and the status of the oil, these three, would have a significant impact on the actual operating conditions and the lifetime of the transformers. Ingress of moisture from atmosphere and degradation of insulation, that is solid insulation rather, these two factors are the main sources of water to increase in transformer insulation system. It is also important to note that the solid insulation made of cellulose fiber would have to interact well with the water molecules, which always have to stay in it with an insoluble state. As the transformer system, it has been exhibited that most of the water molecules that are not to be in oil but actually trapped in the solid insulation, that is paper and pressboard part. With the rise of temperature, these water molecules is then forced out from paper to the oil. As due to constant change of loading profile of the transformer with having instant variation of temperature, it is quite evident that the water content of oil and paper insulation would never be at the equilibrium condition. Most important. Migration of water molecules from paper to oil and vice versa would have to depend on the variation of temperature profile in respect of transformer loading cycle. At the elevated temperature, the weak hydroxyl bonds that would have been dissociated easily and the moisture is thus to migrate into oil. While temperature would have been dropped down as due to reduction of running load, the moisture is then start to migrate into the cellulosic insulation from the liquid dielectric. However, this process is completely influenced and guided by the respective absorption limits and solubility limits of the oil and paper insulations. Therefore, initial expedition for moisture ingress and generation of water in the transformer insulation system would have been produced by the chemical reactions involving at its oil and cellulosic insulation. Now, the concept of solubility of water in oil that has to represent on a weight to weight basis, that is milligram of water per kg of oil basis, and has to depend on the condition of the oil, the temperature and the type of oil. Solubility is thus to indicate the total amount of water that can be dissolved in the oil at a specific temperature. So, its value never be constant and would have to change with the change of temperature. The amount of water that can be dissolved in oil would have to be increased with the increase of temperature. However, that increase is not at all linear but exponential in function. The normative references as cited in the international standard IEC 60422, where it is clearly mentioned the desirable moisture levels for the newly built oil immersed power transformers. During the manufacturing process, transformers should have to be dried up until the moisture content in the cellulosic insulation would have been gone down less than 0.5% in mass, and in case of oil, about 1% water in mass or even less would be an acceptable level. As the paper is highly hygroscopic in nature, so it is quite necessary to become dry and then impregnated with oil under vacuum to reduce the water content below 0.5%. However, exactness of moisture content at the insulation system that should be categorically executed in relation to the contractual requirements defined between the manufacturer and the purchaser. As of the reference IEC 60422, where it is suggested that for new transformers of above 170 kV, prior to energization, the maximum permissible concentration of water in oil should be within the limit of 10 milligram per kg. From the relevant research data, where it is shown that when a transformer is in overloaded or short-circuited condition, where the temperature of the winding conductor, if escalated at a speed exceeding the speed at which water vapor dissolves in the oil, then there would have to generate micro bubbles, which may appear from 100 degrees centigrade onwards. Insulation papers that are usually made of wooden pulp fibers, which are then thus to be staggered to form the composite thickness as required. During the staggering application, there may have the possibility of incomplete bonding of fibers in the paper, which leads to have some certain gaps or pores. Porosity in cellulose structure that would cause to store excessive amount of water molecules in cellulose insulation system. Under such condition, Water vapor bubbles as developed in the composite insulation system oil and paper would therefore be divided into two categories. One, water vapor, and B, other gases mainly include nitrogen, oxygen, carbon monoxide, various low molecular hydrocarbons, etc. So, the amount of water vapor and gases that would have to increase significantly with the rise of temperature. With rise of temperature, the dielectric strength of those evolved gases as relative to oil or cellulose would have been extremely low, so such phenomenon would significantly impair the transformer's insulation system. It is quite evident that solid insulation has a basic tendency to absorb moisture during operation and maintenance of oil immersed transformers. Moisture ridden insulation Moisture ridden insulation could cause bubble effect in turn to turn insulation when the load of transformer increases rapidly with the abrupt rise of temperature. The trajectory of the bubbles would have been affected by the AC electrical field, and its dynamic behavior would be much more erratic if there would have non-uniform electric field. Through the experimental study, it has been established that the bubble generation characteristics of oil paper insulation system is significantly influenced by certain factors such as moisture content, rate of rise of temperature, gas volume fraction, air pressure, and electric field. If the evolved gas bubbles generated in large quantity, then a change of bubbles that can be formed in a region of high electrical stress, that is, the windings and leads, resulting in sharp decrease of oil and paper dielectric integrity. Sharp decrease of oil and paper dielectric integrity. The case would have been much more serious when the evolution of thermal bubble formation would be in strong electrical field, as because that could easily lead to the partial discharge in turn to turn insulation. Such occurrence that may have even lead to insulation breakdown in oil paper insulation system. Analyzing the degree of risk while at short time emergency overloading of transformer, it is quite ethical to consider the winding hotspot temperature, which must not be exceeded an incipient bubble temperature. According to IEC 60076-7 2005, where it is recommended to use of thermally upgraded paper that has been chemically treated to improve the stability of cellulose structure. Such type of paper is very sensitive to temperature, and in case of short time emergency overloading, it can have to withstand a hot spot temperature of 140 degrees centigrade. The aging acceleration factor of this thermally upgraded paper is found to be about 100, which means 1 hour to withstand a hot spot temperature of 140 degrees centigrade is equivalent to 100 hours at the rated temperature. So, in that case, the bubbles are likely to occur when the hotspot temperature exceeds 140 degrees centigrade for a transformer with a winding insulation moisture content of about 2%. However, this critical temperature of conductor wrapping paper would have to decrease as the moisture concentration increases. In fact, a chain of bubbles can also be formed at the surface of the heavy metallic parts, which are being heated by the leakage flux or would have been produced due to supersaturation of the oil. These metallic parts are not in connection with the core and windings and would have been insulated with non-cellulosic insulation such as aramid paper, glass fiber, etc. But the layer of gas bubbles would have to form on these non-cellulosic paper insulations as due to rapid rise of temperature of the water contaminated liquid insulation. The moisture related parameters and temperature limits are thus to be well specified in IEEE or IEC guidelines, where it is categorically mentioned that rise of temperature never be exceeded to 180 degrees centigrade. According to the IEC standard 60076-7, the winding hotspot temperature would be taken as the critical temperature limit up to which transformer can operate safely, and its value must always be below the bubble inception temperature. Important. Now, the bubble initiation temperature would have to depend on many factors. One, active water content of the paper, that is cellulosic paper, insulation at the interface with the oil. Two, water content of oil at the interface between the interface with the paper insulation. First one, active water content of paper insulation at the interface with the oil. Second one, water content of oil at the interface with the paper insulation. Number three, capillary property of paper insulation. The capillary property of cellulosic paper insulation refers to its ability to absorb and release of liquids, particularly water, through tiny channels, or micropores within the cellulose fibers due to the surface tension of the liquid. Number four, gas voids in paper insulation. Number five, surface tension of oil. Number six, temperature gradient of oil paper interface. Number seven, rate of temperature rise. Number eight, static head pressure of the liquid above the area of bubble formation. 9, dissolved gas content of oil. Number 10, short-term or long-term overload. 11, partial blockage of the oil channel within the windings. Number 12, failure of the cooling system. All these are being to involve the bubble initiation temperature. The bubble effect initiation temperature can be referred as a particular temperature at which vapor bubbles would have to start forming within the insulating oil paper system. From the research, it has been revealed that the bubble effect phenomenon and its initiation temperature parameter would have to depend mostly on the active water content level in the cellulosic structure of the solid insulation. It is well established. It is well established that the higher be the water content level in the cellulosic structure, there would cause an abrupt drop in the bubble initiation temperature. So, there would have a major correlation in between the water content as exists in the cellulose mineral oil insulation system, and their composite temperature profile with respect to increase of load. When the water content is high, that can result in saturated vapor pressure, and the vapor is to saturate more quickly in liquid dielectric, which thus to impact on the bubbling initiation temperature. However, with the rise of temperature, the surface tension of an insulating liquid that would have to reduce, which would cause to decrease the inside pressure of the bubble. The surface tension of insulating oil is an important indicator as a force that causes a liquid to minimize its surface area, and that plays a crucial role in the formation and stability of bubbles. It is as because that the pressure inside the bubble is always be in higher state than the pressure outside due to the surface tension causing to pull the bubble surface inward. However, certain factors are responsible to directly affect the surface tension of a dielectric fluid, causing an obvious impact on its bubble inception temperature and generation of microbubbles. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions could encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.